So when we looked at this equation last week, I asked you to go through and predict the products. Okay, do the double replacement. Okay, and I said that there were two answers that we could provide. The first answer, the official answer, we could have gotten away with just writing NR. Okay. The other unofficial answer was doing the actual full double replacement reaction. Okay. What does NR mean? No reaction. Okay, so now we know what it means. Why am I allowed to write no reaction instead of going through and showing all those products? What is our reaction supposed to be? A chemical reaction. How do we know a chemical reaction has occurred?
Change in phase.
Change in phase. Do we see a change in phase? No. Everything is aqueous. That means no chemical reaction occurred, so we can write it as no reaction.
So that was my question. Because of both acids that are not reacting.
That's where the acid term is coming up. Sorry, it just clicked. So I'm hearing reference to these being acids. How many of those four compounds are acids? Absolutely none of them. What is the definition of an acid? Hydrogen first, followed by aqueous at the end. These, yes, are all aqueous, but none of them have a hydrogen to start, so they aren't acids. Okay. So they're all aqueous, which means no phase change. No phase change means no chemical reaction. So we could write it as NR.
Okay, so that was like it goes, like when you see that they remain as an aqueous phase.
Yep. Which then begs the question: if you were just told to predict the products, okay, you could write NR, but how did we know it was NR? How did we know there was no reaction? There was no phase change. No phase change on what? What are the products? Have we done the double replacement yet? No. So without actually doing the double replacement and looking at what those products are and evaluating their solubilities, if we don't do any of that, we can't jump to no reaction. Okay? It is only after doing the double replacement, showing what those products are, specifying their phases, can we then state that that reaction is a non-reaction, and we could then write it as NR. Okay? So it's a bit of a cheat or a bit obnoxious because we have to go through and do the double replacement to be able to do the prediction. Yes?
So how do you know that like sodium nitrate and lithium chloride are aqueous?
How do we decide sodium nitrate and lithium chloride were aqueous? That was our solubility rules.
Oh, yeah, okay.
Okay? And of those solubility rules, I told you to memorize 3 of them. Okay? Because if you had those 3 memorized, we don't have to go back to them. Rule number 1 said what? What's that? The alkali metals, which happens to be the first column, not row. It's okay. Our first column are alkali metals. Where is sodium? First column. So anything with sodium will be what phase? Aqueous. Where's lithium? First column. Anything with lithium will be aqueous.
Period.
Okay, period. That's why you should memorize that rule. It doesn't change.
So we never have to like guess.
So you will never guess the solubilities. You have to follow rules.
Isn't that salt NaCl? That's
NaCl is a salt, yes.
but it's salt.
What's that?
Isn't salt solid?
Salt, is it solid? Okay, if I brought in a container and it had white solid in it, you might say that was salt. But what happens if I bring in 2 containers? One with a beaker full of water and one with the salt, and I pour the salt into the water. What happens to the salt? It dissolves. Can I refer to that new beaker now as just salt? It's salt water. It has both compounds in it. How do I write it as a formula? Well, the formula for sodium chloride, or salt, is NaCl. How do I include that water's present? That's the AQ. Okay. So the AQ is just saying that water is also involved in this process. It's just not part of the chemical reaction.
So what if the AQ wasn't there?
If the AQ wasn't there, then we'd have to specify what that phase was. Could it have been a solid? Sure. Could I also have liquid salt? Yeah, absolutely. Okay. You can liquefy salt. at stupidly high temperatures, like 900 degrees Celsius. So I could do liquid salt. Okay? Will you ever do liquid salt in your chemistry career? Probably not, because you're not going to be getting that hot. Okay? There's a few that might. Okay? What are you guys doing?
She takes it back a week.
I'm going to walk this way. Questions about that? Questions about our double replacements? Okay, so the next sequence of our slides, we've got roughly 50 slides and 3 lectures, okay, which is likely or easily possible to get through. Some of it will be review. The hardest part in this next sequence of material that we're going to have to worry about is coming up with a formal notation. Okay? That is the biggest part. Okay? You have to have a standardized notation to be able to go through and solve these questions. Not because when I ask how many feet are in 36 inches, how many is that? 3, because you know that conversion. That's an easy thing for you to internalize and have done because you've been doing it for 20 years or 18 years or however many years you've been alive. Okay? But what happens when I say how many moles are in 6.23 times 10 to the 28th atoms of iron?
Yeah, no.
Okay. Until we have a formalized notation, we aren't going to be able to do that conversion. So what you should be focusing on within this section, okay, is coming up with the format for how you solved. Okay? Not the answer. Focus on the format. Okay? So the first unit that we passed through is the PSS chapter because our textbook company wanted more money. So what they did is took the 6th edition and they took a section out of the 2nd chapter and they turned it into the PSS chapter. It's now a new textbook. They can sell it for $400 instead of $200. Sweet. Welcome to the textbook industry. What's up?
I can never find you on campus, so I wanted to give you a baby birthday present.
Thank you.
Happy baby birthday.
Within our significant figure, or that chapter, now I'm all confused and flustered. Thank you, Lorelai. Significant digits are going to be the biggest application. So I posted a quiz because I wanted to see how much you remembered from that very first lab you did on significant digits. Okay? Considering we had, 37 people in this class and 14 people took the quiz. Okay? Not a really good sample size, but it was a last-minute quiz, so that's okay. Okay? Of the 14 people that took it, the average was probably 20% correct. Okay? Which means, guess what? We need to review significant digits and make sure you've got those nailed down. Okay? Because that will become important when we go through and deal with things kind of indirectly. The next part is carrying those significant digits or significant figures. So what are the rules on what makes things significant? How do we use them and propagate them through a calculation? And then we've got this last one, scientific notation, which still ties in with significant figures. Okay? So where this is all coming back to is this extra new concept that is different from mathematics, okay, or a lot of mathematics you may have seen. When you do math, what do you look for? Think back to your math classes and what you've been doing in math classes. What do you typically ask your teacher for? A formula. Okay, the answer is fair enough, but we typically get a formula. Say, how do I solve for the area of a square? I need a formula. What is the formula to do this? Okay. You will probably continue to ask me that in chemistry, and I will tell you there is no formula. Okay. What you need to be tracking are your units. So if you know what the units mean, you don't have to memorize any formulas. It's now just a question of, do your units match on either side of the equation? The units that we will be dealing with are typically distance or length, mass or weight, volume, and time. For our distance or length, what unit will we be looking at? Meters. Okay. There are a variety of units that we could use, but meters is the most common one, okay, and the accepted one that we'll be using this semester. For mass, grams. I guess I could write this out. Grams, meters, volume.
Liters.
Okay, we have liters, and I heard milliliters. That's interesting. Why are two different units? How big is a liter? A lot. Let's go into the lab and let's do an acid-base reaction with a liter of acid and a liter of base. Okay? We're going to end up getting hurt with the amount of chemicals that are getting consumed. That is highly dangerous. So what do? We switch it to a smaller measure of volume. That's our milliliters. Okay? Time. What do we use for time? Seconds. Okay? Seconds is an awfully long word, and you can tell I don't really... Well, actually, I spelled that right, didn't I? We could abbreviate it. How could we abbreviate it? We could say SEC, or, because we're even lazier than that, S. Yep. Liters, we can abbreviate as L. Milliliters. Little m, big L. Why the big L? Because it's liters. It's referencing back to our base unit. Breathe, guys, breathe. It's okay. Grams. G. Meters. M. Are there other units we could use? Yeah. So what does that mean we're going to be expected to be able to do? Convert between all those different units. Exciting. Okay. Not really exciting. I apologize. I don't want to make you feel too excited about that. Okay. The metric system, those are the units we just kind of elaborated. The metric system is our most commonly used one. That's what we're going to spend most of the semester focused on, is the units of the metric system, because they're the most consistent and useful worldwide. Okay. If we're going to do mass, we can determine mass using a balance. We've got a variety of different balances we could use. Which of those three balances have you used? Probably the lower right, I would hope. Okay. Why do we not use the other two?
They're not effective. High school.
Too manually? That, I can kind of accept that. The other two are confusing to use. You have to slide things around. You can kind of do obsolete, but they're actually doing this. Why is the digital one easier to work with? You put it on and it tells you the number. That's why we use that mass. Okay? There is a neat little video here about mass. You could go through and look at it, but we're not going to look at it this time. Sorry for time. Volume. We've got a variety of ways to measure our volume. Okay? We've got graduated cylinders, which we've used in the lab. We have syringes, which we've not used in the lab. Okay? We have burettes. We have pipettes. We have volumetric flasks. All of them are different ways that we can go through and contain a liquid, or theoretically even a gas, and allow us to measure something about it. Why do we not measure the mass of a liquid? What happens when you pour water on your computer? Okay, it cleans it, right? It becomes super clean. We don't have to worry about any data left on the computer because it's all destroyed. Okay, it's all wiped clean from the computer. What are our balances? Our balances are electronic. What happens when we pour water on our electronic balances? It destroys them. Okay? So we want to prevent that, so we come up with another way to measure our liquids. That's where we come up with these different measuring devices. Okay? Then we move into this concept of measurements and uncertainty. When we look at the balances, all of that information is just spit out and given to us. It just tells us a number. But if we were going to measure, say, a length, we need to use a ruler. If we need to measure a volume, we need to use one of those graduated cylinders. So we have to learn how to interpret the instrument appropriately. Okay? So what is the length of that little metal rod? 4 point something. That's nice and vague.
4.2.
4.2
centimeters.
394.
Anybody else?
It's over one, for sure.
Okay.
I would say 4.
Which of those digits is consistent?
4.
4. So all the way through, That number is super important. We have to measure or report that number. What is the first digit that is not consistent?
2, 3, 1.
The tenths place. Okay. Depending on who measures this, that tenths place reading becomes something different. Okay. Why is it something different? What are you doing to get that number? You're guessing. The instant you guess, you stop writing numbers down. So the 7394, the 7 is a guess on top of a guess. How accurate is that going to be? Not very. How about the 3? It's a guess on top of a guess on top of a guess. That's a really bad thing to do. In science, we're trying to be as precise as possible without just complete guesswork. Okay? So this device is accurate to that tenths place. So we could go through and report, say, I already heard someone say it was bigger than 1, so let's say 4.2. And we could go through and include an uncertainty, plus or minus what? So what we do is run 1,000 different tests, and we compare the numbers there. How much do they vary by? 0.1. So plus or minus 0.1. We now have an uncertainty in our measurement, and that information is now given to us, and we know what's happening there. Okay, that's useful. Okay. How often do we report the uncertainty? How many of you saw uncertainty before you started a chem class? Okay, 2 people, yeah. Okay. It's very rarely shown. It is often implied, and it is always included with the instrument if you look at the instrument carefully enough. What if I want more significant digits or more digits? I want to go to 4.25. What has to happen? I need to add in more marks. Nobody count that. I'm going to assume there's 9 lines there. I did it?
Yeah.
Awesome. Look at that. Okay. And now we could add a little bit more information. The 4 is precise. The 2, well, it's bigger than the second hash mark, so the 2 is exact. But now I'm guessing at the next location. Make sense? What this is doing is giving us a measurement. Once we have the measurement, we need to layer on top of that an extra piece of information. That extra piece of information, if I remember correctly, let's ignore that, keep ignoring that, would be our significant digits. We have to be able to look at that measurement and decide how many of those digits are significant. Okay? Well, we took the measurement. It was 4.25. So every single one of those digits is significant because I observed them. I made that measurement. What if you aren't doing the measurement? What if you're given that information? How do you know how many of those digits are significant? There has to be a rule set to apply. This is looking at our significant digits. And you might ask, well, when would I ever use numbers that I was given and not directly measuring? Are you being tested? During that test, every single number is something that you've measured? No, unfortunately, you are given those numbers, so you must interpret those numbers based off of these significant digit rules. When we look at significant digits, we've got a sequence of numbers down here. How many of those digits, or how many significant digits do we have in each? The first one, how many do we have? 1. Second one?
2,
Third one?
3,
Fourth one? 2. Fourth one? 1. We didn't get all that perfect. Why not? Because we aren't appropriately applying our rules. So we need to define what makes a digit significant. And the difference that came through in defining those came down to what? What did we have confusion over labeling as a significant digit?
0.
The 0. And that is because 0 carries 2 different meanings. 0 can carry the meaning of a placeholder. Okay? For instance, these zeros in that last number are acting as placeholders, telling us that the 1 as a significant digit needs to be placed where? In the hundredths place. The zeros are not a number that mean anything. They're just there saying, don't put the 1 there because then it's not in the hundredths place. What about the zero, or the zeros here? What do those zeros mean? They are now significant. Okay, well maybe it's just the location of where they are relative to the decimal point. What about the 0 and 10? It's not significant. Well, what the heck's going on with our rules? How and why can we apply our rules to the meaning of that 0? Is it the not 1 through 9? Or is it not a number? It's just a placeholder. Is it just telling us where to put our other numbers? To decide that, we need to identify our significant digits. 1 through 9 are always significant. There are no exceptions to that. After that, what we have to do is look at the placement of the decimal point. Okay? And that decimal point will dictate the meaning of the 0. Is it a placeholder and meaningless? Okay? Or is it a significant digit? Is it a value that is not 1 through 9? So, we've got a bunch of numbers here. See what you can come up with in the next 4 minutes. So let's take a look at this. So if we start, sigfigs 102. Next one. Next one. So I gotta move. Next one. Ooh, there was a question mark on. Question mark there. We'll go back to that. Next one. I guess we're saying the top by the next one. Next one. Next one. Next one. Okay. So in what people were shouting out, the only one that was challenged was the lower left. Does everybody agree with that?
I don't agree with point 012. Wouldn't that be my significant figure?
Point. This one you're saying? Okay, we'll look at that one too. So we'll look at the bottom too. Good.
I also don't agree with 0.012.
Yeah, for the same reason though.
Yeah.
So I'll star them both. Before we even look at that, I want to address these two. Any ideas why, or let's start with what's the difference? There's an extra 0 there. Does that 0 hold any meaning as a significant figure? No. Is it really doing anything as a placeholder? No, because the decimal is telling us where to put the 1. So why include the 0? Write that value for me. Write 0.12. Seriously, just write it. Write 0.12. Okay, you ready for me to do it too? 0.12. Is that 0.12 or is that 12? No, there's a decimal point. Here, Paisley, you need to verify. See that right there?
Oh, yeah. Oh, my gosh.
There's a decimal point there, right? You can't see that decimal point because you used probably a pencil and you just did dot or a pen and you just hit the paper. When you go back and look at your work, what happens to that dot? You don't see it. What happens if instead of writing 0.12, you write 0.12? And now you look at that and say, why the heck did I put a 0 there? That split-second pause causes you to then do what? Look for the decimal point. And a number that was 0.12 now stays 0.12. Without hitting that paper or making your decimal point large enough to insist on seeing, right, that number can become 12 versus 0.12. Is that going to be a significant difference in your calculation? Yes. Right? So when it comes to work, you will see me circle a number written as 0.12, and you will see written right next to it, usually LZ, for leading 0. Okay? Just telling you, hey, include it. It will help with your calculations. I can't tell you how many times I can look at someone's work and be like, that work is spotless, and you're getting the complete wrong answer, and it usually comes down to the placement of a decimal point. Okay? So putting that 0 in can help minimize that calculation mistake, particularly if you're in a multiple choice exam. After that, we can then shift to the other ones that we were looking at. So column on the far left, why is that 4? Okay, well, we have to use our rules. 1 and 2 are always significant. To decide if the 0 is significant, we have to look at rule 2 and 3. Rule 2 says if there is no decimal point, so immediately stop reading it because you have a decimal point. Move to rule 3. Rule 3 says if there is a decimal point, okay, the 0 needs to be immediately preceded by a significant digit. So we will start at the far left of that number. Well, the 1 and the 2 were significant. Now I need to question the 0. At first 0, I'm going to look immediately to the left, and what do I see? A significant digit, which makes that 0 now a significant digit. We move to the next 0, and it's now a question mark, and I look to its left. What do I see? A significant digit, which was a 0, which then means it's also a significant digit, and I have 4 sig figs. Okay. What happens when we move to the 0.012 or 0.012? It's still a decimal point, so we need to interpret. We'll start with our first 0. We look to the left. What do we see? Nothing. Is that a significant digit then? We move to our next 0. What do we see? We see a 0. We aren't looking for zeros. We're looking for significant digits. Is that a significant digit? No. 1 and 2 are significant. I only have 2 significant digits. Same thing goes down to rule 3. Or sorry, not rule 3, the next one down, which had 3 significant digits. The first 2 will not count because they don't have a significant digit in front. The 1 and the 2 are significant. We look at the last 0. What is immediately in front of it? A significant digit. That makes that 0 significant, and I have 3 sig figs. We good? Okay. You must apply these rules. Okay. When do you apply them? Every time you see a number. Okay. Every time you change a number, you need to use these rules. Every single time. Okay. It will eventually become ingrained. So let's move to the next question. Measurement versus exact. How many quarters are in this picture? And don't start giving me this fraction stuff. Let's assume those are whole quarters. 7. 7 quarters. So what's the question going to be? Yeah, that's a fair question. But try a different one. What were we just talking about? How many significant figures are in the measurement of 7 quarters?
So it's $1. Yeah.
So
$1.35.
is it? That's nice. That has nothing to do with quarters. How many significant digits in that measurement? 1. Okay. So 6.9. That would have 2 significant figures. So what if I was just a fraction off? Can I be just a fraction off of my quarters? No. How many quarters are there? 7. Exactly 7. Which means how many sig figs are there? 6.9 sig quarters? Okay. 7.1 quarters? No. 6 quarters? 6 as a number has only 1 sig fig. Why is it 7? Why is 7 only 1 sig fig? What's that? You can count them physically. That's fine. How does that address our sig figs? It's exact. Which means how many sig figs do we have? We have all of them. Okay. The measurement of 7 quarters is exactly 7 quarters. Not 6.9, not 7.1, not 6.999999999 quarters. It is exactly 7 quarters, which means there are an infinite amount of significant figures in that measurement. And that is because it is an exact value. How often do we encounter exact values? Not super often. They usually come from counting objects. Okay? The number of pens in my hand. Okay, I can count those. There's 2. Not 2.1, okay, not 2.4, 2 pens. There's an infinite amount of sig figs in that measurement. Okay? How many inches in 1 foot? 12. 12.1? No, exactly 12. How many sig figs in that measurement? An infinite amount of significant digits. 1 foot equals 12 inches. Not 1.1, exactly 1 foot. Where does this come up? It is a definition. When do we see exact sig figs or infinite sig figs? In definitions of conversion factors. If we don't have a definition, then we're going to end up with all sorts of potential for adding or losing sig figs. So we have to be careful with that. Our exact values will always have infinite sig figs. So why do we care? Okay. So let's go through and do addition and subtraction. What is the answer for that? We do that, addition, subtraction. Yeah, you thought you could get out of this class without having to do any math. It's coming back really hard. So add it up. Stop looking at the bottom. What is the answer? Okay, well, if we're going to play it that slow, I think I can do it too. So 2, 6, 3, 3, 1, 6, 5. Wasn't that hard, guys? Come on. Right? For those of you that don't want to do the long addition, I'm perfectly all right with that because we have this nifty new device that we call a calculator that can do the addition for you. You are fine to use a calculator. The next question becomes, what do you report as the answer? It follows our rule. Our answer is going to be only as precise as the least precise measurement. Which of those measurements is the least precise? It's the one that reports to the fewest places. Okay? Not the number of sig figs, but the least precise place. I can only report out to, what is that, the 10th place. Which means my answer becomes 115.6 grams. Well, what about the 3362? Didn't my calculator spit that out? Yes, your calculator does not interpret sig figs. You must do that. And for those of you that haven't seen the quiz, let's write down some possible multiple choice answers that you could expect to see on the exam. And I'm tired of writing answers, so we're just going to write those. Those are your answer choices. Anybody have a problem with those answer choices or notice a pattern within those? They're all the same calculator spit out answer. You're just using a different number of significant digits. Okay? You cannot punch stuff into your calculator and say, well, the calculator matches an answer choice. Because guess what? I will punch in all your possible options into the calculator, and I will write those down as possible answer choices. You need to know how you're doing it, not that the answer matches on the list of answers.
So why is the 115.6?
So why do we use just the 115.6? Okay, so we said this is our observation. Okay, why is that important? What do I know about the next digit in that 114.3? I know nothing about it, which means that digit could be what?
Anything.
A 0 or a 9. Okay, why pick 0 and 9? What can you tell me about 0 and 9? Which would you rather have as a paycheck, 0 or 9? 9. Why? They're bigger. That's the biggest difference we could have between those numbers for our possible digits is 0 and 9. What happens if we go through and assume they're zeros? We're going to get the answer that we reported out, the 115,63362. What happens if we assume they're nines? Does that change my answer? Yes. Okay. And if we write out our numbers, because this is kind of a neat observation, but I think it might just be random luck. 115.63362. When we reported a measurement, what did we keep? What's that? Fair enough, you need to be giving me a hard time for dropping the grams unit. When we looked at our uncertainty, when we measured the length of that rod, how many numbers could we use? We used all of the exact values that the instrument obviously gave us, so that every time everybody measured it, those were exactly true. So 115, same in the both. What did we do after we reported the next one? It was a guess. We get one guess. That one guess is that next decimal place. Why? What happened to that decimal place? Depending on whether we use zeros or nines, that number changes. If we include more numbers, what's happening? We're guessing on top of guessing. Okay? And we're doing that within our calculation, not just in the observation. So we have to be very careful that when we go through and run our calculations, that we very carefully monitor it and we only report out the stuff that is consistent. Okay? Our consistency goes up to the tenths place. That tenths place is the first place I get a variability. The first place I get a guess. Okay? Make sense? You're shaking your head. Why are you shaking your head? So we take our numbers, what do we do? Step one, take the numbers and do what? Add them up. It reports out a number. What is that number it gave us? 115.63362. Of those numbers, how many can we keep as significant digits? This follows our addition subtraction rule. We can only report to the least precise place, that is the tenths place. Why do we only report to the tenths place and not include those other numbers? Because if we put in zeros or nines on those, because we have no idea what they are, does that number change? Yes. That is my guess.
So if we do have numbers like all zeros up there.
If you had the numbers all the way out, then how far do you report?
As far as you can.
As far as you can.
Okay. So then,
So you know that, okay. So you
Because they all, in this top calculation, where's our least precise place?
the tenth place. Did I say that right?
Yeah, I don't know all the numbers either. Tenths, hundredths,
Thousands.
thousandths, 10,000ths, 100,000ths. So in that upper right calculation, they all go out to the hundredth, the really small. Okay? Which means we could carry it all the way out.
so that would be the answer, then the 63362.
If that was our measurement, that's what our answer would be, the full thing.
And same goes for the 9.
And the same goes for the bottom one. What those are our examples. What happens if we assumed they were zeros? We can't make that assumption because they could have just as easily been nines. Make sense? All right. Good. I'm glad that makes sense because we're going to make it worse. Go ahead.
I just want to make sure that if it was like 115.66, would you round?
We'll deal with rounding later, but yes. Okay, what happens if we do multiplication and division? What is the area of the square? Okay, so this we could say our math came back and helped us out, gave us a formula. How do we calculate the area of a square? Length times height, length times width, anything like that. Just multiply the numbers. Okay, so we're saying we take 7.28 units, whatever those units are, and we multiply them by 4.6 units. Okay, and when we punch that into the calculator, oh shoot. Did I not really get, I didn't get, oh, there, never mind, the answer's right there. Calculator, punch in, it says 33.488 units squared. Cool. How much of that am I allowed to keep as my final answer?
All of it? 4. Oh, good. It's
33.
33.4.
No, it's just
Right?
33.
I'm hearing 33.5. 33.5 was our addition rule. we go to the least precise place. Well, the least precise place here is our tenths, so we should report out to the tenths. That's when I'm doing addition. Is this addition? No. Does the rule change? Yes. What happens to our rule change? We're only as precise as the measurement with the fewest sigfigs, which means I can only use 2 sigfigs. The answer becomes only 33. Okay. Same idea applies as we did with the last one. Okay. I don't know what that next digit is. It could be 0, it could be 9. Okay. If it's 0, that's the number. If it's 9, what happens? I'd get 34.1432 units squared. Which value is consistent? 30. Which value is my first guess? The ones place, my answer is reported only to 2 sigfigs. Okay? Kind of makes sense? So the rules have meaning behind them on why we hold those sigfigs to be true. Okay? Or why those rules are there.
So even though we have the tenths on that
You
one.
had to do that to me, didn't you?
So even though we had the tenths on that one, we still don't go as far as the tenths.
We don't go out to the tens place. It's a new rule. Our new rule for multiplication and division is we only carry the number of significant digits. How many significant digits are in 4.6? 2. How many significant digits in 7.28? 3. Which one has fewer? 2. My answer must be reported to 2 sigfigs. That takes it down to 33. Okay? Follow the rule. Follow the rule. So when should you round? Okay? What happens if we'd done these calculations? We tweaked the numbers ever so slightly. Okay? For that addition subtraction, how many sigfigs, or what place can I hold my answer true to? How many of those are significant digits? The 1, the 3 are significant. I can only go to the hundredths place because that is the last digit in that top number. Okay? What's the issue about reporting that 3? Okay? It's halfway to becoming a 4. So what should I do to that 3? Keep it a 3 or make it a 4? It depends on the conventions that you're raised with. Unfortunately, the general accepted convention is if it is 5 or larger, you round by 1. And the number becomes 1.34 grams. What happens in the other one? How many sigfigs can I carry through to my multiplication division? Only 2. I look at the first insignificant digit and decide its relationship to 5. I need to add 1, and my answer becomes 37 units squared. I really just hear way easy? Okay. What was that? Okay. It's just a question of continuing to propagate and use the rules. So within that, here's our practice. Okay. For the 14 of you that actually went through and did the quiz, thank you. You now know the wrong answers because you took the quiz. Go through and figure it out. The first 2 questions, I want to know how many sigfigs in that number. For question 3, 4, 5, 6, I want you to do the calculation and report that to the proper number of sigfigs. And if you got questions, raise your hand, I'll come to you. I did leave it up there intentionally. The lower right-hand corner has all the answers. So we'll write it a little bit bigger. Everybody always asks me to write down what the answers are, or I'll ask students to tell me what the answers are, and you take too long, so I had to write them down. So we get 3, 6. I actually revealed that at an inopportune time, because usually I like to do it with something like the division and be like, Yeah, if we carry the 4, divide by the 3, oh, yeah, that's right. We end up with, I think that was approximately 0.454 grams, centimeter cube. Pretend like I can do it in my head. But usually causes people to gasp in amaze and shock. Makes me feel smart. I don't get any other opportunity to. Next one, 4540. At least somebody laughed at that comment. Thank you. And then we had 0.
Wait, what is going on there?
Did I skip one? No, I did it right.
That's not right. You can't have grams from 2 liters.
Oh, I just put the liter on wrong.
No, that's not even right. Yeah.
No, that's right. So that should be all the numbers with the proper units now. There was a question about 4. Is there questions about any of the others? 6. I'm going to call out 5 too. So the question with 4. How many sigfigs are we allowed to carry through to our final answer in 4?
3.
Only 3 because of that number. Okay. It is 3 sigfigs. The 0 counts because I look to the left and what do I have? A significant digit, which makes the 0 significant. I have 3 sigfigs. Okay. I then go to my answer, and what the calculator, I believe, spit out was 4538 point some numbers. Okay. I can only report 3 significant digits, which means the first 3 are significant. Okay. The first insignificant digit, what's its relationship to 5? It's above 5, so I need to add 1. So the tendency for some students is to go through and write, well, this is 454.
Yeah, so why would you have 0?
So let's pause for a second here. Let's assume that was your paycheck. You punch it into the calculator, your paycheck comes out, you get $4,540. I, as your employer, only give you $454 and say, sigfigs, deal with it. Are we going to get a minor revolt there? Yes. That 4 must be in the thousands place. How can I make sure it makes it to the thousands place? I need a placeholder 0 to make sure that that 4 gets placed in the thousands place. Is that 0 significant?
Yes. No.
No, because there's no decimal point. If I had instead written the decimal point, now what happens?
You make it a significant.
Now it's a significant digit, and my answer is wrong. Because I'm now saying it's 454. With 4 significant digits, it's 4538.
So that explains why.
Okay? So you cannot get rid of the 0 because there's something there. There's a placeholder. So that's the question you were asking about 12 versus 200 or 120. Okay? It's a placeholder. It's not an exception. It's a placeholder. Okay? So it is coming down to what those things mean. Somebody had suggested an alternate method to go through and make sure that we can get that number to be 4,000. They suggested we use scientific notation, which we've yet to talk about. That's supposed to be a decimal point, so let's try that again.
Yeah, there you go.
Now I don't have to worry about the 0 at all. I've got clearly 3 sigfigs. This still holds the meaning of 4,000. Okay? So this is one of the reasons why we use scientific notation. When we move to 5, what's an interesting feature in 5? What happened to the number of significant digits? How many sigfigs in 33.12? How many sigfigs in 33.0948? A lot. I appreciate that. The next one, our final answer has how many sigfigs? 1. Okay, the zeros won't count as significant digits because for them to count as significant digits, what must be immediately to the left? A significant digit, which there is none. I start with a whole bunch of sigfigs and I end with only 1 as a final answer. This is an issue with subtraction. When you subtract numbers, you very likely will lose significant digits, which means when we do any kind of scientific measurement where we're going to do a subtraction later with those numbers, we want those numbers to be as different as possible so that we minimize the loss in significant digits. Okay? Last one, our division, 454. Whoops, I left off a 0, it looks like. I think it's 0.0454. This is a division. So Heather, what was your question here on this one? Just how many sigfigs? So I also throw in the units in these cases. Can I do anything to the gram unit? No. Where is the gram unit currently? Numerator, denominator? Numerator. Where should it show up in the answer? Numerator. Where is centimeters cubed? Denominator. Where should it show up in the answer? In the denominator. We leave them alone. Okay. So I've got a couple other big things that I want to put through. We've got all this information now on one slide. These are facts that you need to be able to control, manipulate, and use. Okay? So we can say memorize, but memorizing the fact on its own does nothing for you. You need to be able to manipulate those in new environments, okay? Which is a challenging thing to go through and do. For those of you taking pictures, that's probably a good idea because that has all of the information on it. Okay. That has all of our information on it that we might need. We might wonder, why did Mike not give us this information as a handout? And that would be a bad thing to wonder because I already did. You have the PowerPoints on Canvas. That's why this slide is here. You can just print it off of Canvas. Some mathematics simplifications that I kind of want to whip through here. Okay? If we were to write this down in our notes, 4 times 4 times 4 times 4 times 4 times 4. Okay? You're going to be like, yeah, let's just go ahead and write all that out. How are you saying, yep, I'm going to write it? Okay, why not? We can take care of some mathematical manipulations, and we can use powers. We can use our exponents. We can do that 4 to the 6th. Okay? Sounds like you guys already got that, which is good, because we'll be using exponents a lot in the next unit. Okay? It's going to become even more relevant when we look at our powers of 10. Okay? Yes?
If we're going to the next unit, are we having another test soon?
Yes, you're having another test soon. That's a good question. When is that next test? Next Thursday. This is why you should look at the schedule.
Is there a practice exam?
There's already a practice exam. There's also a practice exam for the final and for the third test.
Wait, how many more tests are there?
Enough. We have to continue on. Powers of 10 allow us to go through and take numbers that are really, really big and make them easier to work with. 10 to the 6th. Okay? Or really, really, really small and make them 10 to the negative 6. The smaller your number, the more negative your power of 10 should become. Okay? We will see our powers of 10 again, I promise, on Thursday, which is why I'm going to skip over it and get to our scientific notation. Okay? Scientific notation is ultimately a lazy way to present a measured value. So the distance between the Earth is 406,300,000 meters. Okay? Or the distance between a carbon atom and an oxygen atom is that much. Thank you. Okay? Repeatedly writing those numbers that small can be very tedious and risk-destroying, just like our exponents. So what we want to go through and do is remove some of that excess writing. Okay? In particular, all of those insignificant zeros that are acting only as placeholders, not as actual numerical values. I want to remove that information or collect it into one pool. That is going to be my power of 10. Okay? My scientific notation is by definition a single digit 1 through 9 in the ones place, followed by a decimal point, followed by all other significant digits. Okay? Then I'll multiply by my power of 10. So if we were going to go through and take a look at, say, that top number, how do we convert that to scientific notation? Well, we start with our first number in the ones place, which happens to be our 4. We'll place a decimal point, and we will follow that by all of our significant digits. Okay? So the 4 is significant, the 6 is significant, the 3 is significant. How about this 0? Yes, because it is trapped between two significant digits. So it is also significant. How about that 0? Okay. Those were some no's that were very softly said over here, for those of you that may not have heard that. 4.063 times what? 10 to the what? We're going to take our implied decimal point. We're going to show how many times it shifted. 1, 2, 3, 4, 5, 6, 7, 8 locations. Sorry, I ran out of screen space. Was my number really big or really small? Really big, which means the sign on that 8 needs to be positive. You do not need to write the positive. How about for the next one? 1.16 times 10 to the 1, 2, 3, 4, 5, 6, 7. 7. Was my number really small or really big? Make it negative. Okay? That's how we manipulate our scientific notation. Okay? Because I really need to get to this, some physicists go through and make these measurements. Okay? How many significant figures are in each measurement? The top one has how many? 4. The next one? 9. The next one? 3. Okay? With that question, how many of you like to interpret your English at the same time you interpret your math? Anybody? Okay. Notice it says 406 million meters. Okay. Do you really want to interpret the English at the same time you're also dealing with mathematics? Okay. So what we need to do is rewrite that number in a fashion that allows me to get rid of the English and make it just math. Okay. So write out the last number using that same number of significant digits. You are only allowed 3 sigfigs. How can you write it out? I like that. 4.06 times 10 to the, was it 8? 8. Okay. Let's actually go through and say, you know what? That scientist actually did a little bit better. He actually measured this top number up here. He actually got 6 significant digits. So some of those zeros are significant. How will he report that number, or she, report that number so that 6 digits are significant? You can't subtract. Change the meaning of the number. Which digits are significant? 4, 6, 3, and that 0. So 4 absolutely are significant. I need 2 more to be significant. Which 2 am I going to make significant? The next 2 zeros need to be significant. How do I rewrite that number so that those are significant digits?
4.06300.
This is why we use scientific notation. It can take zeros that are ambiguous as to whether or not they are significant or not, and now unambiguate. Is that a word? Disambiguate. Okay. Disambiguate, unambiguate, and make sure those zeros are counted as significant figures. You're going to Google it?
Clarify? I would usually.
I don't like clarify. Clarify is too nice. Okay. That is the big end of our scientific notation debate. What we'll be moving into, ignore that quiz. We'll be looking at the metric system in Chapter 2, starting on Thursday. Officially, we talk Tuesday as well, so I'm going to try and burn through content Thursday so that we can review Tuesday. It's ultimately all going back to what are your measurements and how do you convert them.